Okay, we're going to start out here in Chapter 1 of the OpenStax Algebra and Trigonometry book. The link to this book is right here. You can also look up OpenStax on Google and search for Algebra and Trigonometry, however you want to do that. But we're going to begin very early here with some basic arithmetic, and we're going to talk about counting. Now, the history of counting is vague. There's no way really we can know when humans first began counting. I would imagine humans could count right from the inception of humans, but to what extent they counted, that's a different story. But anyways, here is a very early example of some early humans counting. This is the a Shango bone. It's a tally stick from Africa, and it's about 20,000 years ago. And as you can see, what a tally stick is it's a stick of some type, and notches are marked in it, and you can see notches marked in this. Now, what's interesting about this is they even seem to possibly be grouped. So there might have been some more advanced type of counting than we thought, perhaps that long ago. It wouldn't surprise me at all. Now, most historians believe that the earliest systematic form of counting occurred back in ancient Sumeria. Ancient Sumeria, or ancient Sumerian, around 3000 BC. Now, the counting that occurred back then, the Sumerians, they counted with a system called a base 60 system. So we today will start at 1 and we'll count 2, 3, 4, 5, 6, 7, 8, 9. And when we get to 9, we'll call their next number is 10, which is like a placeholder. And then we'll start over again with 11, 12, 13, 14, 15, 16. Well, the Sumerians did the same thing, except they had, and of course, 1 through 9 we have a different symbol for, but we just recycled the symbols from that point on. Well, the ancient Sumerians, they did the same thing ish, except they didn't get to 10 essentially, or they didn't get to the placeholder until after 59. So they had what we call a base 60 system. And that means they had a different symbol for every number up through 59. Just like we have a different symbol for every number up through 9. They had a different number for every number up through 69. Well, this worked well for them because of the geometry basis mathematical society they had. We actually get our time from this. 60 minutes, 60 seconds in a minute, 60 minutes in an hour, this sort of thing is a holdover from that period, the Sumerians 3,000 years ago. This was then adopted by the Babylonians. This is a picture of what a Babylonian gate might look like, similar to the Ishtar Gate, famous Ishtar Gate. But that would have been around 1800 BC. So the sort of counting that's similar to what we do didn't come around until the ancient Egyptians, sometime after this. You can see they used a system very similar to ours, a base 10 system, where you'd count to 9, and they have, you see their symbols over here. Get my drawing pad up. So here they're counting to 9 just like we do, but they have a different set of symbols like these over here. And then when they got to 10, they would place this in front. And when they got to 20, they'd place this. And after 99, they got to 100, they would have a symbol that looked like this placed in the front. So you see a number here, the number 1,328 represented. Well, you would have a 8. So they're actually writing this the reverse direction that we would write. So they'd have an 8, which is 2 lines. And then in the tens, instead of a 20, they would have this little lambda type symbol. So that's next. And then they would have the 300 symbol. That's this. And finally, the 1,000 symbol. So it's just written in the reverse direction. There's nothing to say that the direction we write is the correct direction. It's just the direction we've all decided to write. So our system, though, our system directly evolved from a Hindu-Arabic system. And originally in India, ancient around the 11th century AD, they had the first 9 digits represented, as you can see here, 1, 2, 3, 4, 5, 6, 7, 8, 9, by different symbols. And the ancient Indians were really well versed in math, and most of this has to do with the fact that trade is a big drive to become very adept at mathematics. You need to keep track of how many cows you're trading for how many bushels of wheat, so on and so forth, and who owes you what. Well, over time, these symbols changed, and well, actually, this first symbol set started at 2, but 0 initially was only a placeholder. So this was a placeholder at 10, and it didn't look like the 0 initially, but eventually it became 0, and finally, by around 1522, the numbers, the Arabic numbers, look like we are familiar with right now. And this number set, 1, 2, 3, 4, 5, 6, 7, 8, 9, we call these whole numbers. So and that's the set 1, 2, or I'm sorry, we call these natural numbers. Whole numbers actually has 0 added to it. One, 2, 3, 4, 5, 6, 7, 8, and 9. So once you got to 10, you started over again. 11, 12, 13, 14, 15, 16, and you would count similar to the way the Egyptians counted. Well, in the 5th century AD, an Indian named Brahmagupta came up with the idea of 0 as an actual number and the mathematics associated with using 0 in our arithmetic. And of course, initially it was looked at as just a gimmick, but eventually it became part of our number set, and we call these whole numbers, and we have real uses for 0, real mathematical uses. So we can take these whole numbers and we can stick it on a line, a horizontal line we call a number line, and we can equally space them maybe and represent them on this line and make it go out to an idea, a concept we call infinity. Not really a number, but it's a concept. And since we're thinking that we can go in this direction out to infinity, well, why not extend our numbers in the opposite direction? And because we're going in the opposite direction, we'll put a symbol in front of them, which we call a negative sign. And we can extend them in this direction out to negative infinity. And when we do this with our whole numbers, this set of numbers we now call integers. So they're the positive and negative. So we have like 3 regions now. We have the positive region, we have the negative region, So these are your negative numbers. These are the positive numbers, and this is 0. Well, the ancient Egyptians found that whole numbers and integers weren't enough. They needed to represent things as fractions of these. So they developed fractions, where you'll have a number where you have one integer divided by another integer. So anytime you have a situation like this where you take one integer and you divide it by another integer, we call these rational numbers. Here I have a picture of what's called the Rhine papyrus. The Egyptians used to write on papyrus, which are reeds, pressed reeds, and this is from 1650 BC. And this is like a little math tutorial on how to use fractions. So now we can add to our integers and add more ideas. We're going to add to this. We can add more numbers on here. For example, 1/2 or 3/2 or minus 5/2 or 1/3. And any rational number can be represented by a decimal. You can just take it in your calculator and take the number and divide it by the numerator by the denominator. For example, 1/2 would equal 0.5. 3/2 would equal 1.5. 1/3 would equal 0.33, and that 3 would go on forever. So you can have a decimal that repeats forever, but it's still a rational number because it can be represented by an integer divided by an integer. Well, it wasn't long before people playing around with these numbers recognized something, and there was a group of people in ancient Greek called the Pythagoreans, and they were real geometry-based mathematicians, and they recognized that you have triangles. You can always figure certain things out with these triangles, and especially working with what we call a right triangle, where this line is perpendicular to this line. So this is horizontal and this is vertical line. And then you have what we call a hypotenuse, which is always longer than these two. So they saw that, but they recognized that if you took one side and you squared it, and we'll go into detail about this and prove it later. Another side, well, demonstrate it, not necessarily prove it graphically, and square it, you get what we call the square of this side. Now, we haven't really talked about exponents yet, but we will in a little bit. But problem was, if you set these two sides equal, A and B, you'll end up with a situation where you have 1 plus 1 equals 2, and that's supposed to equal C squared. So that means C equals the square root of 2. Now, if you go to your calculator and you do square root of 2, you're going to get a number, something like 1.412. But really, this number goes on forever. And the fellow who figured this out was named Hippasus. And we're going to continue talking about this in the next video.